I would like to extend a warm welcome to you as you join us on this science channel that is sure to lull you to sleep. I am really happy that you have managed to make your way to this video, as we will be investigating some of the most amazing wonders of the cosmos tonight. No matter where you are in the world, take the time to relax and enjoy this common moment of calm. Allow the noise of the outside world to fade away, and let your thoughts become as calm as the starlight that fades into the darkness of the night. Picture yourself floating peacefully over the night sky, as if you were on a slow journey, passing by planets that are concealed from view, stars that are shining brightly, and galaxies that are ancient. Tonight, we will reveal amazing realities about the cosmos, including its mysteries, wonders, and the fragile threads that connect everything you have ever known. You might be taken by surprise by some of the things you hear, while other discoveries will settle gently in your mind, similar to the way distant light emanates on a peaceful, clear evening. If you find that these non-violent investigations assist you in relaxing or pique your interest, you might want to think about giving them a thumbs up and subscribing. It also assists other weary individuals in navigating their way to this location, one person at a time. However, for the time being, make yourself comfortable as we set out on this tranquil adventure across the cosmos. The number of stars in the universe exceeds the number of grains of sand that exist on every single surface on our entire globe. The number of stars that appear to be sparkling in the night sky seems to go on forever when you stare up at them. Nevertheless, the truth of the matter is far more astonishing. The total number of stars in the universe is greater than the amount of grains of sand found on all of the beaches on Earth when they are combined. Every star is a radiant sphere of plasma, and while some stars are significantly larger or smaller than the Sun in our solar system, all of them shine across distances that are beyond comprehension. The sheer volume of this seemingly endless supply is a testament to the immense size and complexity of the cosmos, where each and every star has the potential to support its own solar system. This is a sobering notion that serves as a reminder of the fact that the universe is actually incomprehensibly immense and abundant. A vast and glorious ocean of light and energy extending beyond what one could possibly imagine. Spanning 93 billion light-years in diameter, the observable universe is vast. However, it is possible that there is a great deal more beyond what we are able to observe. The cosmic horizon that we are bound by restricts the range of our observations to around 93 billion light-years in diameter. The observable universe encompasses all of the galaxies, stars, and stuff that have emitted light that has had sufficient time to reach us since the Big Bang. Nevertheless, this represents just a tiny portion of all that could potentially be in existence. It is probable that space continues to stretch out into infinity, or at least into the indefinite unknown, beyond this observable barrier, and that it is filled with an infinite number of mysteries and galaxies. They persist in being permanently beyond our reach, obscured in darkness and stillness, due to the fact that the light from those far-off regions has not yet had the time to reach us. This barrier of sight is not a physical edge, but rather a reminder of the limitations of human observation and the immense unknown that is still waiting to be discovered. The expansion of space is ongoing, and galaxies are moving farther away from one another with each passing moment. It's not only galaxies that are traveling through space. The expansion of space itself is the reason why they are being carried away from each other. As time passes, the fabric of the universe is expanding, which is causing the distances between galaxies to increase. Picture dots that are drawn on the surface of a balloon as it is being inflated, and imagine that the dots are growing in size as the balloon expands. The distance between each of the dots increases. It is not because they are moving on their own, but rather because the surface itself is expanding. The entire universe is impacted by this cosmic expansion, which has an effect on everything from the way that light travels to the future fate of the cosmos as a whole. The slow but consistent expansion is what is shaping the vast architecture of space and time, which is a never-ending process. The Big Bang was not actually an explosion. despite what it would appear to be. It was the very act of creating and expanding space-time itself. The Big Bang is frequently thought of as a massive explosion that took place in space. However, it was actually a much more significant event. Space and time themselves came into being at that same moment. There was no room to move through, and there was no time to pass before this occurrence occurred. All of a sudden, space began to expand, and time began to tick, which started the process of creating all we know today. This all occurred after the universe was in a state of incredible density and heat. But then, all of a sudden, it began to expand. While this initial expansion did not entail a sudden and explosive growth within an already existing space, it did entail the quick growth of space itself. This idea not only expands the limits of our comprehension, but also serves as a reminder of just how special and enigmatic the beginning of the cosmos really is. Light from the earliest moments of the universe is still present in every part of space today. The cosmic microwave background is a faint glow of microwave radiation that is almost uniform in intensity and permeates the entirety of the universe. The universe had to cool down before photons could move freely without being scattered constantly. This happened over 14 billion years ago, which is also when old light appeared. It is, in essence, a picture of the universe in its early stages of development, as it provides a glimpse into the universe during the Big Bang. This radiation is a goldmine for astronomers because it contains small temperature changes that reveal the seeds of galaxies and the large-scale structure of the universe. In every direction, we are surrounded by the cosmic microwave background, a silent messenger from the very beginning of time. Galaxies are held together by a secret structure that is made up of invisible substance. Dark matter accounts for approximately 85% of the total matter in the cosmos, despite the fact that it does not emit or absorb light. This enigmatic substance functions as a scaffold that is invisible to the naked eye, and it exerts a gravitational pull that keeps galaxies and clusters from falling apart. If there were no dark matter, galaxies would not possess sufficient mass to prevent their stars from drifting away from each other. The only way that we can identify dark matter is through its gravitational effects on light and objects that are visible to us. Mapping this invisible framework is a useful tool for astronomers in their efforts to better comprehend the structure of the cosmos and the genesis of cosmic webs. Dark matter, which is invisible, is essential to the formation of everything that we are able to see. The expansion of the cosmos is being accelerated by a mystery force. Astronomers were surprised to find out that the universe is actually expanding at an accelerating rate, despite the fact that for several decades they had been operating on the assumption that the universe's expansion was gradually slowing down. The source of this unexpected increase in speed is a mysterious phenomenon referred to as dark energy, which is responsible for around 70% of the entire energy content of the cosmos. Over time, galaxies are pushed farther and farther apart from one another at a faster rate as a result of the effects of dark energy, which functions as a repulsive force that works against gravity. It continues to be one of the most significant puzzles in contemporary physics, forcing scientists to reconsider the fundamental principles that control space and time. In order to forecast what will eventually happen to the universe, it is essential to have a solid understanding of dark energy. Whether it will continue to grow indefinitely, slow down, or come to an end in some sort of cosmic event, galaxies are not distributed in a haphazard manner. They are linked together by massive networks of dark matter. Galaxies are components of a huge cosmic web that is knitted together by filaments of dark matter that span across hundreds of millions of light years. Galaxies are clustered together along these enormous threads, and this invisible superstructure is what directs their formation and placement. There are massive gaps, expansive emptinesses, with only a few number of galaxies that exist in between these filaments. The development of galaxies, as well as their interactions and evolution over the course of billions of years, is all influenced by the structure of the cosmic web. Because we are unable to directly observe dark matter, its presence is only made known to us by the gravitational pull that it exerts on the universe. This pull affects the universe's large-scale architecture, which reveals a cosmos that is connected in a huge network that is both delicate and complex. Our solar system is being transported on a massive cosmic voyage by the Milky Way galaxy, which is rotating at a speed of more than 500,000 miles per hour. The Milky Way galaxy, which is where our planet is located, is a massive spiral shape composed of stars, gas, and dust. It is spinning around at an incredible rate of speed. The solar system in which we reside is trapped in this magnificent revolution, which revolves around the center of the galaxy, completing one circle approximately once every 250 million years. It spins at a speed of more than 500,000 miles per hour. We are carried along on this enormous voyage through the spiral arms of the galaxy, past groupings of stars, and through clouds of gas. The fact that there are such enormous distances between stars means that collisions are extraordinarily infrequent, even though stars move at such a dizzying speed. We receive a reminder of the fact that our position in the universe is constantly changing, and that everything is connected to everything else as a result of this cosmic journey. There are instances when galaxies collide and merge in slow, magnificent dances that last for billions of years. Over the course of billions of years, galaxies do not remain unchanged as static islands. Under the effect of gravity, they float around and interact with one another. When two galaxies approach each other closely enough, they initiate a leisurely and graceful dance, which ultimately results in the two galaxies becoming one giant galaxy. These collisions have the potential to cause clouds of gas to compress and collapse, which can then result in the birth of stars in explosive bursts. Although direct collisions between stars are uncommon, gravitational forces are constantly at work, reshaping the structures of the galaxy and potentially contributing to the development of supermassive black holes that are located in the centers of these formations. In around 4 billion years, our own Milky Way galaxy is expected to collide with the Andromeda galaxy, which is located nearby. This collision will result in the formation of a new cosmic city. Driven by supermassive black holes, quasars are some of the most brilliant beacons of light that have been observed from the distant past. Quasars are bright objects that are found in the heart of young galaxies and emit light across billions of light years. Quasars, which are powered by supermassive black holes, consume tremendous amounts of gas and dust. As a result, quasars generate an immense amount of energy, which in many cases is more than the amount of energy emitted by the galaxies in which they are located. Astronomers are able to investigate the early universe as well as the development of black holes because of this powerful radiation. Quasars function as cosmic lighthouses, lighting the intergalactic medium and exposing conditions in the universe's childhood. Due to their tremendous distance and the incredible brilliance that they emit, they are counted among the most intriguing objects in the universe. During the first few moments of the universe's existence, space saw a burst of rapid expansion known as inflation. This expansion occurred at a rate that exceeded the speed of light. The universe went through an exceptional phenomenon known as cosmic inflation within an extremely short period of time following the Big Bang. This period of time was equal to a small fraction of a second. During this brief period of time, space itself grew at an exponential rate, which was faster than the speed of light. The universe has become extremely uniform on a broad scale as a result of this fast expansion, which smoothed out inconsistencies. In addition, it expanded the seeds of galaxies and large-scale structures that we can see today from small quantum fluctuations. Inflation is a fundamental aspect of current cosmology, and it provides substantial insight into the birth and structure of the universe. It also offers solutions to a number of cosmic problems. The universe had been in a state of darkness and stillness for a long time, but the first stars brought an end to that period of darkness and silence. They illuminated the cosmos for the first time in history. The universe was an enormous, dark expanse with no stars to illuminate the way for hundreds of millions of years after the Big Bang. After that, the first stars, which were enormous and radiant, lit up, shattering the darkness that permeated the cosmos. These old stars generated significantly more heat and burnt through their fuel at a much faster rate than the majority of stars do today. In the process, they created the first heavier elements in their cores. The fog that had been obscuring the area began to dissipate as a result of the surrounding hydrogen gas being reorganized by the strong radiation that they were giving off. This also allowed ultraviolet light to pass through the region without being blocked. The universe was once a cold, dark nothingness. However, during the period known as cosmic dawn, it underwent a transformation that turned it into a lively, light-filled cosmos. This era laid the foundation for the development of galaxies, planets, and eventually life itself. The cataclysmic events of the cosmos are the source of high-energy particles that travel through space at speeds that are close to those of light. Atomic nuclei that have been pushed to extremely high velocities by some of the most powerful and violent events in the cosmos, as well as charged particles, the majority of which are protons, make up cosmic rays. These particles are hurled across the universe at speeds that approach the speed of light by exploding stars, also known as supernovae, as well as by black holes that are brimming with energy. When cosmic rays arrive at Earth, they collide with atoms in our atmosphere, which causes showers of secondary particles to form. The chemical composition of the atmosphere may be affected by these energetic visits, which may also have an impact on cloud formation and climate. Despite the fact that cosmic rays are unseen and enigmatic, they provide a direct connection between us and the most significant events that occur in the universe. There are thousands more galaxies that are close to ours, and they are all part of a vast supercluster that our galaxy is also a member of. The Lanakia supercluster is a massive structure that contains thousands of galaxies that are held together by gravity, and the Milky Way galaxy is one of the galaxies that makes up this supercluster. This vast network of galaxies that travels through space in unison is spread out across hundreds of millions of light-years and is known as a cosmic metropolis. The supercluster known as Laniakea has an enormous gravitational attraction, which influences the way that galaxies interact, collide, and develop within its boundaries. Astronomers are able to gain a better understanding of the processes that are shaping the universe and the universe's large-scale structure as a result of their knowledge of our galaxy's place in this huge cosmic community. Clusters of galaxies are separated by enormous vacant expanses called voids, which span millions of light-years in distance. There are large cosmic voids, which are enormous regions that have a very low density of matter and a small number of galaxies, located in the vast space that lies between the dense clusters and filaments of galaxies. These gaps, which have the potential to stretch across more than 10 million light-years, can have an impact on the way galaxies move and cluster around them. Even though they are almost completely empty, voids nonetheless contain a small amount of dark matter and gas. The large-scale structure of the universe is influenced by their presence, which carves out the cosmic web and has an impact on the dynamics of cosmic expansion. Researching gaps is helpful in illuminating basic mysteries of the universe, such as the distribution of matter and the nature of dark energy. Neutrinos, which are subatomic particles that are almost impossible to detect, are constantly passing through all matter, including your own body. The sun, exploding stars, and other cosmic phenomena are responsible for the creation of neutrinos. These particles are extremely small and have almost no mass. Despite this, they are produced in incredibly large quantities. These particles, which are ethereal in nature, interact with matter very little. They go through your body and even through entire planets without leaving any trace of their passing. Every second, trillions of neutrinos pass through your body, silently connecting us to the energetic activities that take place throughout the universe. In order to detect them, it is necessary to use extremely sensitive equipment that is placed deep beneath the ground or under the ice. Neutrinos, despite being difficult to detect, provide us with a distinct and special understanding of stellar explosions, the inner workings of the Sun, and the fundamental laws of physics. When the cosmos is observed from the biggest possible scale, it appears to be extraordinarily consistent in every direction. The universe looks to be astonishingly uniform when it is observed from a great distance. Regardless of the location we choose to view, the distribution of galaxies and matter does not indicate that any direction is favored over another. The fact that this cosmic isotropy is accompanied by homogeneity indicates that when viewed from the greatest possible size, the universe appears to be almost the same at all locations. This idea is the foundation upon which the majority of current cosmology is built, making our models of how the universe has evolved more straightforward. This extraordinary uniformity on a vast scale is strongly supported by observations of the cosmic microwave background radiation, which suggests that there are basic symmetries present in nature. Space is filled with a sea of neutrinos that are really old, relics that date back to the first few seconds after the Big Bang. Neutrinos were released into the universe in massive quantities almost immediately following the Big Bang. The particles are extremely small and have almost no mass, but they seldom interact with anything at all. Ever since their decoupling from other matter within the first second of their existence, these neutrinos have been flowing through space, resulting in the formation of a cosmic neutrino background. These particles are extremely difficult to detect because, in contrast to light, they are able to flow through nearly everything without encountering any resistance. In spite of this, their presence has an impact on the evolution of the universe and the formation of structures on a huge scale. If we were able to detect and interpret these relic neutrinos, we would be able to gain a glimpse into the earliest moments of the universe, which would provide us with insights into the fundamental laws of physics and the conditions that existed fractions of a second after the Big Bang. Bang! The Hubble constant, which is a tool that scientists employ today, is used to calculate the pace at which the universe is expanding. Since the cosmos was born in a cataclysmic explosion, it has been expanding. The Hubble constant is a measure of the present rate at which this expansion is occurring. This value is a kind of cosmic speedometer, since it connects the speed at which galaxies are traveling away from us with the distance they are from us. On the other hand, determining the exact value of the Hubble constant has proven to be a difficult task, as the many techniques that have been employed have produced values that are marginally different from one another. The continuing research that is being conducted is driven by this tension in measurements, since having an understanding of the precise rate assists us in comprehending the age, size, and ultimate fate of the universe. The Hubble constant is an essential parameter in cosmology, and it serves as the foundation of our comprehension of the expansion of the universe and the history of the cosmos. Redshift is a phenomenon that occurs when galaxies migrate away from one another and their light extends to longer wavelengths, causing it to seem more red. The expansion of the universe causes galaxies to drift farther and farther away from us, and the light that they emit becomes stretched into wavelengths that are longer and redder. This phenomenon is referred to as redshift. This is analogous to the Doppler effect with sound, in which the pitch of a siren that is going by decreases as it moves away from the listener. Redshift is not only useful for informing us that the universe is expanding, but it also provides astronomers with a means of measuring the distance to distant galaxies, as well as looking back in time. Scientists are able to piece together the history of cosmic expansion and gain an understanding of how the cosmos has changed over billions of years by examining redshift. The cosmic distance ladder is a way that scientists have developed for measuring the enormous distances in the cosmos. This method involves a series of steps. Due to the fact that objects are so far away, it is impossible to measure distances in the universe with only basic equipment. As a result, sophisticated methods are necessary for this task. A collection of interrelated techniques, which are referred to as the cosmic distance ladder, is the foundation of the procedures that astronomers depend on. Each technique builds on the one before it. They begin by employing parallax to measure the distances between themselves and stars that are close by. In order to determine the distance to objects that are even farther away, standard candles such as supernovae and Cepheid variables, whose true brightness is already known, can be utilized. Scientists are able to map the immensity of the cosmos with precision when they use this layered methodology. This method assists us in comprehending the scale of cosmic structures and the timeline of the evolution of the universe. The cosmic horizon is the boundary that represents the farthest reaches of the universe that we are able to witness. Beyond this boundary lies the realm of the unknown, due to the fact that the cosmos is about 13. Light that originates from beyond a certain distance has not had time to reach us yet, as it has just been 8 billion years since the beginning of time. The observable universe is defined by this barrier, which is referred to as the cosmic horizon. The sphere that surrounds us and that holds all of the things that are visible. There may be an infinite number of galaxies and mysteries that lie beyond this horizon, but they will remain out of grasp for all eternity. The horizon progressively extends over time, slowly revealing more of the cosmos as it does so. However, the cosmic horizon serves as a reminder that there are boundaries to what we know, encouraging us to maintain a sense of humility and awe as we continue to study the cosmos. The formation of stars and planets is heavily dependent on the presence of little grains of cosmic dust, which roam through space. The minuscule particles that constitute cosmic dust are made up of elements such as carbon, silicon, and metals. Despite the fact that these grains are extremely tiny, they have a disproportionately large impact on the life cycle of the cosmos. Gravity exerts a force that brings stuff together within the dense clouds of gas and dust, and the dust aids in the cooling of these clouds by radiating heat, which in turn enables them to collapse even deeper. The formation of new stars is the end result of this process. Over time, dust grains collide and stick together around young stars, eventually resulting in the formation of planets, moons, and other celestial bodies. In addition, dust offers surfaces upon which complex molecules can assemble, so promoting the chemistry that is necessary for the existence of life. The stars that were first to appear in the universe were almost entirely of hydrogen and helium, with no heavier elements present. The Big Bang was responsible for the creation of the simplest elements, which are hydrogen and helium. These elements were then used to construct the primordial clouds that gave rise to the earliest stars, which are known as population 2 stars. The radiation produced by these stars was extremely potent, since they were enormous and burnt at a higher temperature than the majority of stars that exist today. They had short, spectacular lives before exploding in a supernova, scattering the first heavier elements such as carbon, oxygen, and iron into space. The heavier elements that were present at the time went on to become the fundamental components that were used to construct stars, planets, and eventually all life forms in the generations that followed. Although none of these original stars are still in existence today, their tumultuous deaths laid the groundwork for everything that we are able to see in the cosmos today, and they also contributed to the chemical complexity of the universe. Galaxies located far away shine strongly in infrared light, but they are concealed from view by cosmic dust. There are numerous galaxies that are situated a great distance away from us. These galaxies are concealed by dense clouds of cosmic dust, which prevent visible light from passing through them. This makes it impossible for optical telescopes to detect them. On the other hand, this dust is capable of absorbing energy from intense star formation and re-emitting it as infrared radiation. Astronomers are able to look through the dust and expose places where stars are being born at a rapid rate by observing these galaxies in infrared light. These dusty star-forming galaxies offer critical information regarding the history of galaxies and the expansion of the early cosmos. Scientists are able to have a more complete understanding of the evolution of stars and galaxies over the course of billions of years by examining these objects. It is possible that the weather on Earth is subtly influenced by cosmic rays, which are high-energy particles that originate in space. Cosmic rays are particles that travel at high speeds, the majority of which are protons. These particles are accelerated by cosmic events that are extremely powerful, such as supernovas and active galactic nuclei. They generate showers of secondary particles when they collide with the atmosphere of the Earth, which causes atoms and molecules to ionize. According to some experts, ionization of this kind has an impact on cloud formation, which could have an effect on weather and climate patterns. Cosmic rays serve as a connection between the way the atmosphere of Earth behaves and the energetic processes that occur in the universe, despite the fact that the precise effects of cosmic rays are still a matter of contention. This connection serves as a reminder of the extent to which our planet is connected to the rest of the cosmos. The universe is predominantly made up of matter. However, the question of why antimatter vanished is still a big enigma. The Big Bang should have resulted in the creation of equal quantities of matter and antimatter, which, upon coming into contact with one another, completely destroy each other. Still, the vast majority of our universe is made up of matter, and there is almost no antimatter. The scientific community is greatly perplexed by this imbalance, which is referred to as the baryon asymmetry. It implies that there were certain events that occurred in the early universe that are now unknown to us, and that these processes made it easier for matter to survive. In order to provide an explanation for why anything exists in the first place, it is imperative that one comprehend this mystery. It is still considered to be one of the most profound unanswered questions in physics and cosmology, and it ranges in scale from galaxies and stars to planets and life. The ancient light that we witness now has been subtly marked by gravity. When light travels across the cosmos, it comes close to extremely large objects like galaxies and clusters. These things have a gravitational pull that bends and distorts the course of the light. Gravitational lensing is the name given to this phenomenon. These imperceptible shifts leave behind microscopic distortions in the cosmic microwave background radiation, which is the oldest light that we are able to perceive. Astronomers are able to create a map of the distribution of both visible and dark matter by doing research on these aberrations. As a result, gravitational lensing provides a strong tool for comprehending the organization of the cosmos, as well as the invisible factors that influence its development. The gravity of really large objects causes light to undergo a slight distortion and stretching as it travels across space. Powerful gravitational fields are generated by enormous astronomical phenomena such as black holes and galaxy clusters. These forces cause the path of light that passes close by to bend. This bending gravitational lensing has the ability to magnify and distort images of galaxies that are far away, sometimes resulting in the formation of arcs, rings, or numerous images. This natural magnification functions in a similar way to a telescope in space, giving astronomers the ability to see galaxies that would otherwise be too faint or too far away to see. In addition, gravitational lensing gives a one-of-a-kind tool for studying dark matter, which generates a gravitational pull but does not produce any light. This enables us to uncover the hidden structure of the cosmos. The formation of galaxies and stars marked the beginning of the universe's first light. The age of cosmic dawn began when the first stars in the cosmos lit. This occurred after the Big Bang, following hundreds of millions of years of darkness. For the first time ever, the cosmos was filled with light thanks to the collective glow of these pioneering stars, which banded together to form early galaxies. In doing so, they were able to penetrate the darkness and illuminate the universe. The appearance of this ancient light signaled the beginning of a major transition. It signified the conclusion of the cosmic dark ages and initiated a series of processes that eventually resulted in the intricate cosmic structures that we observe today. This first light provided the groundwork for the creation of galaxies, star clusters, and eventually planets, giving the universe its first look at brilliance. When hydrogen gas was ionized by UV light, the universe became transparent. During the first few years of its existence, the cosmos was a hazy expanse that was filled with neutral hydrogen gas. This gas absorbed a significant portion of the light that was attempting to pass through it. This was altered when the first stars and galaxies came into existence, as their ultraviolet radiation ionized the hydrogen atoms that were in the surrounding area. This process stripped the atoms of electrons and transformed the gas into plasma. As a result of this reionization phase, the cosmic fog was cleaned away, which allowed light to stream uninhibited across space. This change from an opaque region to a transparent one created an opportunity for the universe to show through with clarity, which allowed the huge cosmic web of galaxies to develop and be witnessed billions of years later. During a cosmic high noon that occurred billions of years ago, the rate of star production reached its highest point. Cosmic high noon is the name that is commonly given to the time when there was a massive surge in the birth of stars in the cosmos. This event occurred billions of years ago. Galaxies were producing stars at a rate that was significantly greater than the rate at which they are produced in the present day. This was the case throughout this period in time. The universe was enriched with heavier elements as a result of this rapid increase in the number of stars that were being born, and these elements are required for the formation of planets and life. Subsequent to this peak, there was a steady decrease in the generation of new stars, which resulted in the more tranquil universe that we see today. The evolution of the cosmos was molded by this golden era, which wove the fabric of matter that supports galaxies, solar systems, and, ultimately, life itself. As stars lived their lives and met their eventual ends, elements that are heavier than helium became increasingly common. The first elements to appear in the cosmos were largely hydrogen and helium, which were formed as a result of the Big Bang. On the other hand, the stars underwent a process of fusion of these light elements into heavier elements, such as carbon, oxygen, and iron, within their cores as they were formed and matured. These heavier metals were dispersed throughout space, thereby enriching the interstellar medium when huge stars burst as supernovae. Thanks to this cosmic recycling, each successive generation of stars and planets was able to form out of material that was richer than the previous generation. Eventually, this process resulted in the creation of the building blocks that were required for complicated chemistry and, ultimately, for the development of life. The universe began as a simple primordial soup, but over the course of billions of years, it evolved into an environment that is chemically diverse. A vast network of clusters of galaxies is connected by giant filaments of matter resembling a cosmic web. The universe's large-scale structure is similar to a massive web, with clusters of galaxies connected by gigantic filaments of matter that span millions of light-years. The fundamental pillars of the universe are made up of these filaments, which are primarily composed of dark matter and gas. These filaments serve as guides for the motion and expansion of galaxies. There are enormous expanses of unoccupied space located in the gaps between these strands. The complex architecture of the cosmos is shown by this cosmic web, which influences the way that galaxies grow and form clusters. Mapping these filaments allows scientists to gain a better understanding of the distribution of stuff in the universe, as well as the processes that have shaped the cosmos. Supermassive black holes are responsible for the emission of incredibly powerful jets of particles. Supermassive black holes are located at the center of many galaxies, and some of these black holes release jets of charged particles that fly at speeds that are close to the speed of light. These jets have the ability to stretch for millions of light years, which means that they can have an impact on the gas and dust that are present in the galaxies that host them. They control the rate at which stars develop and have an impact on how galaxies evolve by heating up and pushing away material. The observation of these high-energy jets provides a window into the dynamic interplay between black holes and their surrounding cosmic surroundings. It also highlights some of the most powerful occurrences in the universe. The most dense nodes of the cosmic web are formed by clusters of galaxies that are enormous. The most massive objects in the universe that are tied together only by gravity are known as galaxy clusters. These clusters contain hundreds or even thousands of galaxies that are packed into areas that span millions of light years across. These clusters serve as the nodes that are the most dense inside the expansive cosmic web. A vast and extensive network of filaments constructed from dark matter and gas, which links galaxies together over distances that are beyond our capacity to comprehend. The speed, interaction, and evolution of galaxies are all affected by the enormous gravitational attraction and clusters, which draw galaxies together. These regions are not only characterized by their dynamic complexity, but are also filled with gas that emits hot X-rays, which further contributes to their complexity. Investigating clusters of galaxies provides insights into the distribution of matter on the biggest scales and provides clues regarding dark matter, dark energy, and the history of the universe. Rather than being shaped like a sphere, the cosmos is almost perfectly flat. The geometry of the universe is remarkably flat, according to cosmological measurements, which indicates that it does neither bend inward like a sphere nor outward like a saddle. The flatness of the cosmos suggests that there exists a very specific ratio between the overall energy of the universe and the rate at which it is expanding. Parallel lines will remain parallel even across cosmic distances if the universe is flat, which will then influence the pathways that light and matter take. This discovery lends credence to inflationary theories that forecast this kind of geometry and contributes to the determination of the universe's ultimate destiny, indicating that it will continue to expand indefinitely rather than collapse in on itself. In order to gain a better understanding of how the universe came to be, it is essential to know the shape of the cosmos. All of the cosmic formations were seeded by the minute variations in temperature that were present in light from the ancient past. There are very slight differences in temperature within the cosmic microwave background radiation, which appears to be almost uniform. These changes measure only a few millionths of a degree. The subtle variations in density that existed in the early universe are represented by these little ripples. Over the course of billions of years, gravity amplified these minor differences, which led to the formation of galaxies as a result of matter clumping together, clusters, and the vast, intricate network of cosmic structures that span the universe. In essence, these ancient oscillations represent the initial blueprint of the cosmos, and they are responsible for determining how cosmic structures grew and evolved over time. When one does the math for them, one has a glimpse into the early stages of the universe and the underlying physics that govern it. Due to the fact that we only have the ability to see a single universe, there is a certain amount of uncertainty in our measurements. One of the fundamental limitations of cosmology is cosmic variance, which arises from the fact that there is only one world that is accessible to humans. Due to the fact that we are limited to observation of our own singular cosmic environment, statistical studies of galaxy distributions or cosmic background oscillations are subject to limitations that are inherent to the process. We are unable to be clear about whether patterns that we have noticed are universal or if they are simply the result of chance unless we have more than one universe to compare them against. This uncertainty presents a problem to astronomers as it requires them to create intricate models and conduct thorough analyses in order to guarantee that the results they reach are sound. The fact that there is cosmic variance serves as a reminder that each of us is in a unique position to see the cosmos and that there are boundaries to what we can know about it. Scientists determine the age of distant galaxies by measuring them, and they use this data to estimate the history of the cosmos. By analyzing the light that comes from galaxies that are far away, astronomers are able to estimate how old these galaxies are, which is essentially like taking a trip back in time. Through the study of stellar populations and spectra, astronomers are able to establish the amount of time that has elapsed since these galaxies first began producing stars. Because it takes billions of years for light to reach us, watching galaxies that are far away from us allows us to see the history of the universe over the course of epochs. These estimations of age are beneficial in the construction of a timeline of events that have occurred in the cosmos. which keeps track of the development of galaxies, the rates at which stars are formed, and the evolution of chemicals. When combined with other data, estimating the ages of galaxies provides a complete picture of how the cosmos has evolved from its earliest beginnings to the complex structures we see today. It is possible that hypothetical cosmic strings are remnants of the universe's earliest moments. According to the predictions made by certain physics models of the early cosmos, cosmic strings are one-dimensional flaws in space-time that are purely speculative. Imagine that fractions of a second after the Big Bang, during phase transitions, extremely thin and incredibly dense filaments stretched out over the cosmos, forming what would be the universe. If these strings were to be shown to be real, they could generate gravitational waves or induce aberrations in the cosmic microwave background. Significant insights into the fundamental laws of physics and the environment of the early cosmos would be provided by the detection of cosmic strings. Cosmic strings, which provide a connection between quantum physics and cosmic structure, continue to be an intriguing hypothesis in the field of cosmology, despite the fact that no direct proof of their existence has been discovered so far. Black holes that are located far away and are consuming matter emit high-energy X-rays that shine. Supermassive black holes, which frequently possess millions or billions of times the mass of our Sun, are hidden deep inside the cores of a large number of galaxies. These celestial giants are known to actively consume the gas and dust that surrounds them. When this occurs, the material is transformed into a spinning accretion disk, which is heated to millions of degrees by friction and gravity. The intense X-rays that are emitted by this environment, which is extremely harsh, are able to beam across billions of light-years and can be detected by telescopes in space. These X-rays are crucial in the understanding of black holes by astronomers. They provide insights on black hole growth, their energetic feedback on galaxies, and the role they play in the evolution of the cosmos. They also disclose violent processes that are occurring in close proximity to the event horizon of black holes. These radiant beacons offer a glimpse into some of the most extreme and enigmatic corners of the universe. The development of stars is influenced by the presence of turbulent gas clouds that are located inside galaxies. The gravitational pull of galaxies causes massive clouds of gas to swirl around in a chaotic manner. Shock waves that emanate from supernova and magnetic forces. As a result of this turbulence, certain segments of the clouds become compressed, which causes dense pockets to collapse and ignite, resulting in the formation of new stars. The number of stars that are created and the size that they eventually reach are determined by the equilibrium that exists between gravitational force and turbulence. The life cycle of a galaxy is governed by this complex ballet of erratic movements and calm collapses. Understanding this turbulence is essential for deciphering how galaxies evolve and maintain the production of stars across billions of years, which will provide a vivid picture of cosmic birthplaces. Radio waves that are transmitting throughout the universe are being sent out by pulsars and galaxies that are located far away. Pulsars generate beams of radio waves that sweep over space like cosmic lighthouses. They are neutron stars that spin at a high rate of speed and are left behind following explosions of enormous stars. In addition to pulsars, numerous galaxies emit diffuse radio waves as a result of high-energy processes, such as the creation of stars and the jets that emanate from black holes. These signals are captured by radio astronomy, which reveals previously unseen parts of the universe that are not apparent in visible light. Scientists are able to investigate the large-scale structure of the cosmos, map magnetic fields, and examine unusual objects because of these radio waves. By listening to this symphony, which is played on an invisible radio, one can have a better understanding of the dynamic and energetic character of the universe. Cosmic rays are particles that are discharged by exploding stars and travel at high velocities through space. Cosmic rays are generated when enormous stars reach the end of their lives and explode as supernovas. This process releases shock waves, which speed up particles, primarily protons and atomic nuclei, to almost the speed of light. These particles, which possess a high level of energy, travel across the galaxy and occasionally come into contact with the atmosphere of Earth. When this happens, they cause cascades of secondary particles to be produced, which can be detected by equipment. The chemistry and physics of the interstellar medium, as well as possibly the atmosphere of Earth, are affected by cosmic rays. Earth is linked to catastrophic cosmic events that are far away through their origins and properties. These origins and properties act as messengers from some of the most energetic phenomena in the universe. The patterns in the polarization of ancient light provide insight into the events that occurred early in the history of the cosmos. In addition to its weak glow, the cosmic microwave background radiation, which is the residual radiation from the Big Bang, displays a phenomenon known as polarization, in which light waves oscillate preferentially in particular directions. This modest polarization stores information about gravitational waves and density fluctuations that occurred during the initial moments of the universe. Scientists put ideas of cosmic inflation to the test and get an understanding of the process by which minuscule quantum ripples transformed into the enormous structures of galaxies and clusters through the examination of these patterns. A distinctive window into the physics that govern the origin of the universe and the forces that have shaped its evolution is provided by these subtle signals. The universe became transparent as a result of ultraviolet radiation clearing away hazy gas. In the early cosmos, the hydrogen gas that surrounded the earliest stars rendered the universe opaque. The powerful ultraviolet light emitted by these stars ionized the hydrogen gas after they formed, which allowed light to pass through the gas and made the universe transparent. The universe was transformed from a hazy, light-absorbing expanse into a transparent expanse where photons could move freely as a result of this process, which is referred to as rionization. This process took electrons from hydrogen atoms. Light was able to travel across great distances as a result of this fundamental transformation, which revealed galaxies and structures billions of years later. Rionization is a significant turning point in the history of the universe. It symbolizes the moment when the universe's windows were opened, which set the stage for the evolution of the universe into the star-filled sky that we see today. The early universe was transformed by the earliest galaxies, which ionized hydrogen. The first galaxies were formed when the cosmos emerged from the darkness, and they emitted tremendous ultraviolet light, which ionized the hydrogen gas that was in the surrounding area. The universe, which had previously been in a condition of neutrality and fog, transitioned into a state of transparency as a result of this ionization, which took electrons from hydrogen atoms. For the first time, this process, which is known as reionization, made it possible for light to travel freely through space, which resulted in the illumination of the cosmos and the revelation of the large-scale structure of galaxies. The appearance of the universe was completely modified by the ionizing power of these early galaxies, and this phenomenon marked a significant milestone in the formation of the cosmos. Scientists are able to gain a better understanding of how the cosmos was changed by the first light objects and how they laid the groundwork for the intricate structures that we see today by studying this transition. The expansion of the cosmos is being accelerated because of the unexplained force that dark energy is exerting. An astonishing discovery has demonstrated that, despite the fact that gravity draws everything together, the expansion of the universe is happening at an increasing rate, propelled by a mysterious force known as dark energy. This dark energy, which is responsible for around 70% of the total energy in the universe, behaves in a manner similar to a repulsive pressure, causing galaxies to move away from one another at a rate that increases over time. One of the most significant scientific puzzles that continues to perplex researchers is the nature of dark energy. Our understanding of physics is challenged by its nature, its origin, and the ultimate implications it has on cosmic fate. It has still to be determined whether dark energy will cause the universe to expand indefinitely or whether it will result in a cosmic apocalypse. In the field of modern cosmology, one of the primary objectives is to solve the mysteries surrounding it. The scale factor is a measure of the expansion of distances in the cosmos as time passes. In order to monitor the expansion of the universe, cosmologists make use of the scale factor, which is a measure of the stretching of space itself. As time passes, this dimensionless number changes, thus providing a description of the relative expansion that has occurred since the Big Bang. The distances between galaxies increase by approximately the same factor as the scale factor, which demonstrates that the universe is expanding. Scientists can gain a better understanding of the history of the universe's expansion, the impact of dark energy, and the dynamics of cosmic acceleration by measuring the changes that it undergoes. The scale factor provides a method that is both straightforward and effective for charting the massive unfolding of the cosmos over the course of billions of years. The general shape of the cosmos, as well as its fate, is influenced by the curvature of the universe. The overall density of matter and energy in the cosmos is the determining factor in whether its geometry is flat, open, or closed. When the universe is flat, this means that parallel lines remain parallel to each other even when they are viewed on a cosmic scale. This also indicates that there is a balance between the force of gravity and the expansion of the universe. The universe would go on expanding forever if it were saddle-shaped and open, whereas it would ultimately collapse if it were curved like a sphere and closed. The prevailing data indicate that the universe is remarkably near to being flat, which is changing the way we interpret the evolution of the cosmos. The destiny of the cosmos, as well as the routes of light and matter that guide the grand cosmic journey, are all influenced by this curvature. When it comes to the biggest cosmic sizes, the distribution of matter is uniform. Matter, which includes galaxies and dark matter, exhibits an astonishing degree of uniformity when it is observed on scales that stretch across hundreds of millions of light-years. On the largest scales, this homogeneity implies that statistically, no place is either significantly more densely populated or significantly less densely populated than another. The fact that there is such an even distribution makes cosmological models easier to understand and lends credence to the cosmological principle, which asserts that the cosmos is both homogeneous and isotropic. Despite the fact that galaxies form clusters in certain areas and voids exist in others, the general cosmic balance demonstrates underlying symmetries and structures that regulate the history of the universe. When viewed in all directions, the cosmos appears to be almost identical. Regardless of the direction in which we look, the cosmos appears to be nearly the same, which is what is meant by the term cosmic isotropy. The cosmic microwave background, as well as other observations, provides evidence that there is a uniform distribution of matter and temperature throughout the sky. The foundation for the present cosmological concept of the universe's large-scale structure is formed by the combination of this isotropy with homogeneity. It implies that the rules of physics and the conditions of the cosmos are consistent throughout space, which enables scientists to create universal models that describe the history of the cosmos, its expansion, and its evolution. The Big Bang theory was proven to be correct by the finding of cosmic background radiation. The cosmic microwave background, which is known today as the cosmic microwave background, was first found in 1965 by physicists Arno Penzias and Robert Wilson. It was a chance discovery that occurred when they stumbled onto a faint, uniform glow of microwaves that seemed to be pervading the entire cosmos. Background radiation. This light, which is ancient, is the afterglow of the Big Bang. It dates back roughly 14 billion years to the time when the universe first became transparent. The field of cosmology was changed from a speculative science to a science based on evidence as a result of the discovery of this, which offered strong support for the Big Bang idea. The detailed observations of this radiation exposed the presence of minuscule temperature variations which served as the seeds for the development of galaxies and other large-scale structures. The cosmic microwave background, CMB, continues to be a fundamental aspect of our understanding of the cosmos. It serves as a time capsule from the universe's earliest stages of development and as a guide to the evolution of the universe. The history of the universe encompasses periods of time ranging from fractions of a second to billions of years. In the merest fraction of a second, the universe's tale started. This moment, known as the Planck epoch, occurred immediately after the Big Bang and is almost beyond comprehension in its brevity. The cosmic history of the universe was revealed through epochs that originated from this fiery beginning. Inflation, recombination, cosmic dawn, and the birth of galaxies. Significant changes were brought about at each level. Space is expanding, matter is cooling, light is emerging, and structures are forming. Over the course of billions of years, galaxies went through a process of evolution, stars were formed, and planets took on their current forms. The cosmos is constantly evolving, and this enormous timeline demonstrates that fact. Every instant is part of an endless cosmic dance that links the past, present, and future together. Comprehending this timeline assists us in comprehending our position in the overarching scheme of things. The cosmic light horizon continues to expand, and as it does so, the observable universe extends as well. The cosmic light horizon serves as the boundary for the observable cosmos, the furthest distance from which light has traveled to reach us since the Big Bang occurred. With the passage of each day, this horizon gradually widens, which allows us to observe galaxies and structures that are located at greater distances. Nevertheless, as a result of the expansion of the universe, there are certain areas that will always be beyond our reach. This expanding horizon is an indication of the boundaries of human comprehension and observation. It serves as a reminder that despite the fact that we have witnessed the unfathomable depths of outer space, there is still a significant portion of the universe that remains shrouded in darkness, patiently awaiting future discoveries that will further expand our sense of wonder and awe. For a few moments at a time, space is illuminated by short, intense bursts of energy. Gamma-ray bursts are brief but extremely powerful blasts of light that are so strong that they are brighter than entire galaxies. Collapsing huge stars or merging neutron stars are frequently the cause of these bursts, which can last anywhere from milliseconds to minutes. Gamma-ray bursts are characterized by their transient existence, yet they nonetheless emit an enormous amount of energy, which lights up the most remote regions of the cosmos. They act as beacons in the cosmos, shedding light on the death of stars, the birth of black holes, and the history of the universe. Scientists are able to investigate extreme physics under conditions that it would be hard to recreate on Earth by observing these short but potent outbursts. As light passes through space that is expanding, it is stretched out. The phenomenon known as cosmological redshift is the result of the stretching of light waves as they travel through space. This is due to the fact that the universe is constantly expanding, which causes the wavelengths of light to increase. Galaxies that are far away appear to be redder than they actually are because this stretching causes light to shift toward the red end of the spectrum. Astronomers are able to use redshift as a cosmic clock, which allows them to monitor the rate at which galaxies are receding and to determine the distances between galaxies. The expansion of the universe is directly supported by this phenomenon, which also allows us to travel back in time and observe galaxies as they appeared billions of years ago. The stretching of light is a modest but profound characteristic of cosmic evolution. Since the universe was barely a single second old, relic neutrinos have occupied every inch of space. Following the Big Bang, the cosmos was flooded with relic neutrinos almost instantly. These are incredibly small particles that are so light that they are practically massless and interact with matter only on very rare occasions. In the short period of 1 second, these neutrinos separated from the hot plasma that was contained therein, and they have been flowing across space ever since. The history of the universe and the formation of large-scale structures are both influenced by relic neutrinos, despite the fact that they are extremely difficult to detect because of the weak interactions they have with other particles. They are a representation of a cosmic fossil, and they carry knowledge about the conditions that prevailed in the cosmos during its first stages of existence. The study and discovery of these neutrinos continues to be a primary objective in the field of physics. This endeavor is expected to provide key findings that will shed light on the fundamental nature of the cosmos. Extremely large expanses of space that are devoid of any matter and are found between galaxy clusters are referred to as cosmic voids. Cosmic voids are enormous expanses of space that span millions of light years. These regions are sparsely populated due to the fact that there are few galaxies or matter present. These massive empty spaces can be thought of as cosmic deserts, and they stand in stark contrast to tightly packed galaxy clusters and filaments. Despite being largely empty, voids are essential to the formation of the universe's large-scale structure because they have an effect on the gravitational pole and the movements of galaxies that are located nearby. Scientists are able to gain a better understanding of the distribution of dark matter, the impacts of dark energy, and the general evolution of cosmic architecture by studying voids. The expansive, silent spaces that we see serve as a reminder of the immense scale of the cosmos and the complex relationship that exists between matter and empty space. Over the course of billions of years, galaxies gradually merge together, which causes them to expand in size. Galaxies are entities that are always changing as they mature and develop through the process of merging with galaxies that are nearby. Slow and majestic, these galactic mergers are events that take place over the course of billions of years, during which time stars, gas, and dark matter come together. Mergers between galaxies have the potential to drive bursts of star formation, alter the structure of galaxies, and provide fuel for the black holes that are located at the centers of galaxies. It is anticipated that in a few billion years from now, our very own Milky Way galaxy will crash and merge with the Andromeda Galaxy, which is located in close proximity to us. A comprehension of galaxy mergers provides insight into the methods by which the structures of the cosmos get more complicated over the passage of time, thereby presenting an image of a universe undergoing perpetual change. The movement of charged particles is influenced by invisible magnetic fields that run through galaxies. Despite the fact that magnetic fields are invisible, they are present across galaxies and have an effect on cosmic processes. The movement of charged particles is guided by these fields, which also have an impact on the formation of stars and influence the way that interstellar gas behaves. While they are very feeble in comparison to the magnetic field of Earth, galactic magnetic fields extend for thousands of light years, winding their way through spiral arms and galactic halos. The investigation of these magnetic forces provides astronomers with a better understanding of the dynamics of galaxies, the propagation of cosmic rays, and the ways in which matter and energy interact with one another on a large scale. These threads, which are not visible to the naked eye, contribute to the intricate nature of the cosmic tapestry. Mutations in DNA that are seen on Earth are sometimes caused by cosmic rays. Supernovae and other occurrences that occur in space are the sources of cosmic rays, which are particles that possess a great deal of energy. When they collide with the atmosphere of the Earth, they generate showers of secondary particles that make their way to the surface. On occasion, these particles can infiltrate live creatures, which can lead to DNA alterations. The majority of mutations are either innocuous or are fixed. However, there are a few that play a part in the evolution and genetic variety of species. The biological history of Earth is connected to the cosmos at large by the continuous rain of cosmic rays, which demonstrates how subtle cosmic events affect life on our planet. During the early cosmic phase transitions, objects that resembled bubbles may have evolved. During the universe's initial moments, there may have been sudden changes that are referred to as phase transitions. These changes may have caused the formation of bubble-like formations in space-time. The expansion and collision of these bubbles might have produced gravitational waves or left traces on the cosmic microwave background. As the cosmos cooled down, fundamental forces began to separate and symmetries began to break down. These phase transitions are related to these phenomena. The discovery of evidence of these bubbles would be a significant contribution to the field of high-energy physics. It would also provide insight into the conditions that existed immediately following the Big Bang, giving us a glimpse into the fiery start of the universe. The origins of our cosmos are revealed by little variations in the light from past times. The seeds that eventually lead to the formation of all cosmic structures are carried by the cosmic microwave background radiation, which is composed of weak ripples or minute variations in temperature and density. These small variances are representative of the slight disparities in matter concentration that existed in the early universe. Over the course of billions of years, gravity amplified these discrepancies, resulting in the formation of galaxies, clusters, and cosmic filaments. Scientists are able to decipher the conditions that existed at the beginning of the universe and test cosmological ideas by mapping these fluctuations with exquisite precision. These delicate marks provide us with a deep and meaningful glimpse into the origins of the universe, as well as the forces that are driving its evolution. The northern and southern lights, which are seen near Earth's poles, are formed with the assistance of cosmic rays. Cosmic rays, which are high-energy particles that fly through space, are one of the factors that contribute to the formation of the magnificent auroras, which are also known as the northern and southern lights. These particles become excited when they collide with Earth's magnetic field and atmosphere in the vicinity of the poles, which causes gases to shine in brilliant hues of green, red, and purple. The upper atmosphere becomes energized by cosmic rays and solar wind particles, which results in the creation of dazzling light shows that are so captivating. This cosmic connection between Earth's skies and distant energetic events serves as a reminder that our planet is a part of a large and dynamic universe in which subtle cosmic influences shape natural wonders. Galaxies are carried along by gravitational currents, the shapes of which are determined by the distribution of matter. Although the movement of galaxies appears to be random, they actually travel along huge gravitational currents that are determined by the way the universe distributes stuff, with dark matter being of particular importance. Galaxies are guided along filaments of the cosmic web by these invisible fluxes, which urge them toward dense clusters and holes in space. Over the course of billions of years, this cosmic dance has influenced the birth of galaxies, their interactions, and their evolution. Astronomers are able to map the large-scale structure of the universe and discover the forces that are driving cosmic evolution by gaining an understanding of these gravitational streams. This allows them to see how matter is connected to itself at the largest stages of the cosmos. The last time that photons were scattered was approximately 3,800,000 years after the Big Bang occurred. Photons, which are particles of light, were able to separate from matter and move freely across the cosmos when it had cooled down to a certain degree. This occurred approximately 380,000 years after the Big Bang. The discharge of the cosmic microwave background radiation, which is the earliest light that can be seen today, is celebrated by this event, which is known as recombination. Prior to this point in time, the universe was opaque due to the fact that charged particles and photons were constantly engaging in interactions with one another. The universe was turned into a translucent expanse at the instant of the final scattering, which enabled light to travel across space and time. The early conditions of the universe, as well as the structural changes it has undergone, can be discovered by studying this light. Minor fluctuations in temperature in galaxies and clusters of galaxies that are seeded by ancient light. The cosmic microwave background radiation is almost completely uniform, although it does have extremely small variations in temperature that are only a millionth of a degree. These little differences are associated with density oscillations in the early universe. These distinctions were made even more pronounced by gravity over the course of billions of years, which resulted in the clumping of matter and the formation of galaxies, clusters, and the cosmic web. The universe's large-scale structure is established by these primordial seeds, which provide the groundwork for its future. Through the accurate charting of these fluctuations in temperature, scientists are able to get a deeper understanding of the early stages of the universe, as well as the mechanisms that have contributed to its history. Over the course of time, galaxies are stretched and shaped by gravitational tides. In the same way that the tides on Earth are affected by the gravitational force of the Moon. Gravitational forces from nearby galaxies and dark matter cause tidal effects in galaxies themselves. The spiral arms and star formation patterns of galaxies are influenced by these gravitational tides, which are responsible for stretching, distorting, and reshaping galaxies. Tidal interactions have the potential to spark bursts of starbirth or possibly lead to galactic mergers over the course of millions of years. Understanding these tidal forces allows us to gain insight into the ways in which galaxies develop and change over time within their cosmic surroundings. It also brings attention to the dynamic and interconnected nature of the universe as a whole. Galaxies and clusters developed from quantum fluctuations that occurred during the inflationary period. The Big Bang was followed by a short period of cosmic inflation, during which time quantum fluctuations, which are differences in energy that are extremely small, increased in size at an extremely quick rate until they reached cosmic proportions. All of the galaxies and clusters that exist today sprang from the seeds that were formed by these fluctuations. Inflation caused these ripples, which were barely noticeable, to become much more pronounced, and they were permanently etched into the fabric of spacetime as a result. Over the course of billions of years, gravity has magnified these variances, resulting in the diverse cosmic formations that are observable today. This extraordinary process demonstrates the tremendous connectivity of nature's tiniest and greatest scales by connecting the quantum world to the expanse of the universe. Stars and planets develop from cosmic dust grains, which are sometimes known as seeds. The life cycle of the universe depends on the existence of little grains of cosmic dust that float through the space between stars. These grains are made up of elements such as carbon, silicon, and metals. These dust particles come together to form enormous clouds, which cool the gas and make it possible for it to collapse under the force of gravity. This collapse results in the emergence of new stars, while the material that surrounds them comes together to form disks, which have the potential to become moons, planets, and other heavenly bodies. Dust also stimulates complicated chemical reactions, which result in the creation of chemicals that are fundamental to life. Despite their extremely small size, these cosmic grains constitute the foundation of stars, planets, and, eventually, the complex fabric of the cosmos. Distances that are too great to be measured in conventional units are measured in light years. Light travels a distance of approximately 6 trillion miles, or 10 trillion kilometers, in 1 year. This amount is known as a light year and is a useful unit of measurement for calculating distances in space. Astronomers are able to characterize the distance between us and other celestial objects, such as stars and galaxies, by using light years to measure the distance. This measurement helps us to understand the vast scope of the universe. To illustrate, the closest star that is not our Sun is located more than 4 light-years away from us, which means that it takes more than 4 years for the light from that star to reach us. Light years give us a feeling of both cosmic time and distance by making a connection between the immense size of space and the speed at which light travels. The light that is the oldest in the cosmos has a temperature that is only a few degrees higher than absolute zero. The universe's oldest light, known as the cosmic microwave background radiation, is a phenomenon that penetrates all of space. The temperature of this radiation is incredibly cold, with a value of approximately 2.7 degrees above absolute zero. What remains of the hot and dense early universe after it has cooled down is the dim glow that we see today. As space expanded over the course of billions of years, it stretched and chilled. In addition to having a temperature that is almost perfectly consistent, it has minuscule oscillations that gave rise to the structures that exist in the cosmos. The frigid temperature serves as a reminder of the transformation that the universe has undergone, transitioning from a flaming start to the wide, chilly state that it currently exhibits. It is a silent, pervasive glow that embodies the passage of cosmic time. Showers of cosmic rays are constantly cascading down through Earth's atmosphere. Air showers are cascades of secondary particles that are formed when high-energy cosmic rays, which are particles that travel at speeds close to the speed of light, come into contact with atoms in Earth's atmosphere. These showers of rain are distributed throughout the atmosphere, and they occasionally make their way to the surface of the Earth, where they are observed by detectors all around the world. Showers of cosmic rays offer valuable insights into the most energy-intensive processes that occur in the cosmos, such as the formation of black hole jets and supernovas. In addition to that, they interact with the chemistry of the atmosphere and may have an impact on climate patterns. The constant barrage of cosmic rays that showers down on us is a reminder of the fact that Earth is linked to the greater cosmic environment. The motion and growth of galaxies that are located in their proximity are affected by voids. The dynamics of neighboring clusters and galaxies are influenced by cosmic voids, which are enormous areas that contain just a small number of galaxies. The gravitational effects that their low density produces cause the matter that is in the vicinity to be pushed in an outward direction. This has an impact on the flow and grouping of galaxies in the universe. The evolution of the cosmic web is shaped by the presence of voids, which influence the creation and interaction of galaxies as well as the direction in which matter moves along filaments. The study of voids assists astronomers in comprehending the function of dark energy as well as the structure of the cosmos on a vast scale. Despite the fact that these boundless expanses appear to be devoid of life, they play a subtle but significant function in the formation of the cosmos. The galaxies that hold black holes are shaped by the jets of material that emanate from them. It is common for supermassive black holes that are located in the centers of galaxies to release strong jets of charged particles that are moving at speeds that are close to the speed of light. The influence that these jets exert over their environment stems from their ability to heat and disperse gas, which allows them to extend for millions of light years. Black hole jets are responsible for shaping the interstellar medium and regulating star formation, and in doing so, they play a role in the evolution and growth of the galaxies that contain them, effectively functioning as cosmic sculptors. Insights about the interaction between black holes and galaxies can be gleaned by observing these jets, which indicate dynamic processes that are responsible for forming the grand design of the universe. The period of time that is referred to as the cosmic dawn is when the first galaxies were born. The period of time known as the cosmic dawn is considered to be among the most significant and transformative epochs in the history of the universe. After hundreds of millions of years of darkness, the moment that the first galaxies lit signaled the beginning of a new era. The first clusters of stars and galaxies were created as primordial clouds of gas collapsed under the force of gravity during this epoch. The cosmos was inundated with ultraviolet light as a result of the proliferation of these newly formed galaxies. This led to the start of processes such as reionization, which ultimately brought about changes in the cosmic landscape. With the arrival of this dawn, the cosmic dark ages have come to an end, and the universe has begun a new chapter in its history, a chapter that will be filled with light. An examination of this time period provides insight into the manner in which the most fundamental building blocks went through a process of evolution to become the intricate cosmic structures that currently occupy the sky. This investigation also provides a look into the universe's awakening from its original state of stillness. The universe's most ancient light permeates the majority of the available space in a somewhat consistent manner. The entire universe is bathed in a faint, almost uniform glow of cosmic microwave background radiation. This ancient light is estimated to have originated around 14 billion years ago, a vestige of the time when the universe first started to become transparent. It is quite impressive in its homogeneity. Over the course of enormous distances, the temperature only deviates by minuscule fractions of a degree. The even, almost uniform glow that we observe now is a reflection of the smoothness of the early cosmos after the Big Bang, before gravity began to amplify the subtle perturbations and turn them into galaxies, clusters, and filaments. We are all surrounded by this all-encompassing light, which serves as a silent witness to the universe's early stages of development and is the basis upon which the structure of the cosmos was created. We are connected to the beginnings of the cosmos through this cosmic backdrop. Scientists are able to map out the history of the universe with the help of measurements of the ages of galaxies. When scientists examine the light that is emitted by galaxies that are billions of light years away, they are essentially looking into the past. By doing this, they are able to estimate the age of these systems that are so far away. The ages of the stars within these galaxies may be determined by examining their spectral signatures. This information provides insight into the evolution of galaxies and the time at which star creation first commenced. This cosmic archaeology makes it possible to assemble the timeline of galaxy development, chemical enrichment, and star birth rates, which is a difficult task. Measuring the ages of galaxies, when combined with other measurements, gives a complete narrative of cosmic history, illustrating how matter has developed from a hot, dense beginning to the intricately organized cosmos we observe today. The continual story of cosmic transformation and development is revealed through the use of this technology. The process of cosmic evolution is a description of the way that all things undergo change over the course of billions of years. The epic tale of alteration from the universe's fiery beginning to its current state is known as cosmic evolution. It involves the development and growth of stars, galaxies, and planets, as well as the beginning of chemical complexity. Fundamental forces have been responsible for the shaping of matter and energy over the course of billions of years, and the result is the molding of the cosmos into complex forms. The galaxies, star populations, and cosmic settings that are always changing serve as a reflection of this continuous transformation. Understanding the evolution of the cosmos allows us to gain a more comprehensive understanding of our position in this vast and ever-changing universe. A universe that is in a perpetual state of expansion, change, and revelation of its mysteries over the course of time. We are reminded that we only observe one universe by the fact that there is cosmic variance. One of the fundamental limitations in the field of cosmology is known as cosmic variance. It is caused by the fact that humans are only able to view one world at a time. Astronomers are tasked with the responsibility of analyzing data from a single cosmic realization, which is in contrast to experiments in which it is feasible to conduct repeated trials. As a result, measurements that are based on statistics, such as the fluctuations in the cosmic microwave background or the distributions of galaxies, are always going to have intrinsic uncertainties. It is possible that some of the characteristics that have been identified are merely random variations as opposed to universal truths. The obstacles that scientists have when they attempt to distinguish between signal and noise are brought to light by cosmic variance, which also emphasizes the distinctive perspective that mankind possesses when it comes to investigating the cosmos. It serves as a reminder of the humbling reality that our ability to observe is limited. The solar wind, which is a stream of charged particles that is constantly being emitted by the sun, interacts with cosmic rays. The solar wind, which is a steady stream of charged particles that are emitted from the sun, comes into contact with incoming cosmic rays, thus impacting the number of them that make it to Earth's atmosphere. This interaction has an effect on the level of ionization in the upper atmosphere and contributes to space weather occurrences by modulating the strength of cosmic rays. This modulation is affected by fluctuations in solar activity, which results in changes in the flux of cosmic rays over the course of solar cycles. In order to safeguard satellites, astronauts, and the technology on Earth from the harm radiation might cause, it is necessary to comprehend this intricate interaction. In addition, it demonstrates the relationship between solar behavior and cosmic effects, highlighting the ways in which our star interacts with the greater cosmos through subtle but significant processes. Galaxies are shaped by the magnetic fields that span their whole length, and these fields also influence how they change throughout time. Magnetic fields, which are imperceptible yet powerful, permeate galaxies in their entirety. They influence the manner in which charged particles move and the way in which interstellar gas behaves. These fields assist in the regulation of star formation by directing the flow of gas and having an impact on the collapse of clouds, which is where stars come into being. Galactic magnetic fields, which span thousands of light-years, become entangled with cosmic rays and plasma, hence increasing the complexity of galactic dynamics. Despite their relative weakness in comparison to the magnetic field of the Earth, they have a significant effect on the evolution of galaxies due to their sheer size. Astronomers are able to have a better understanding of how galaxies evolve, maintain their structure, and interact with their surroundings over the course of billions of years if they have a solid grasp of these magnetic forces. The universe became transparent to ultraviolet light as a result of ionization. During the early stages of the cosmos, ultraviolet light was absorbed by neutral hydrogen gas, which made space appear to be dark and opaque. This hydrogen was ionized by the powerful ultraviolet light that was emitted by the first stars and galaxies, which resulted in the gas being transformed into a translucent plasma when electrons were stripped away. For the first time in the history of the universe, light was able to flow freely across the cosmos since the cosmic fog had been lifted during this epoch of ionization. This transition brought about a profound change in the way the universe appeared and made it possible for the intricate structures that can be seen today to form. The study of ionization provides insight into the earliest luminous objects and the processes that led to the clearing of the cosmic haze. The universe's childhood, which was characterized by darkness and opacity, was brought to an end with the arrival of cosmic dawn. The universe's departure from a state of darkness and opacity is a hallmark of the era known as cosmic dawn. The cosmos was shrouded in darkness and mist before this period because it was filled with neutral hydrogen gas that soaked up light. As the first stars and galaxies came into being, strong radiation started to ionize hydrogen. This process cleared away the fog, allowing light to pass through space. The transformation of the universe into the translucent expanse that we perceive today was brought about by this dawn of cosmic illumination. Astronomers are able to gain a better understanding of the time, mechanics, and effects of the universe's initial illumination by exploring cosmic dawn. If cosmic strings do indeed exist, they may be able to disclose secrets about the fundamentals of physics. Cosmic threads are hypothetical faults in the fabric of space-time that are exceedingly thin. A few hypotheses regarding the first moments of the universe predict that cosmic strings may exist. If these filaments, which are exceedingly dense, are real, they have the potential to spread across enormous distances in space, thereby impacting gravitational fields and potentially resulting in the generation of gravitational waves that may be detected. Detecting cosmic strings might provide profound insights into fundamental physics, including the unification of forces and the fabric of space-time itself. Cosmic strings continue to be an intriguing idea that might serve as a link between quantum mechanics and cosmology, despite the fact that there is no concrete evidence to support their existence. The reason that the cosmos appears to be smooth and uniform when seen on a wide scale is due to inflation. The hypothesis of cosmic inflation puts forth the idea that, moments after the Big Bang, there was a short period of time in which the universe expanded at an exponential rate. This quick stretching process was able to smooth out any imperfections and distribute the minute quantum fluctuations across a huge distance. One explanation for the reason why the cosmos appears to be so consistent in all directions despite its massive scale is the phenomenon of inflation. These insignificant variations turned into the seeds that would eventually grow into galaxies and other structures on a massive scale. Inflation is still a foundational element of contemporary cosmology since it resolves a number of mysteries that are present in the cosmos. It connects the most minute scales of quantum physics with the largest cosmic structures. The messages that were sent forth during the universe's birth are carried by photons that were released during the Big Bang. For about 14 billion years, photons, which are particles of light that were produced at the Big Bang, have been traveling through space. The cosmic microwave background radiation, which is a faint glow that fills the universe, is made up of these ancient photons. Information regarding the first moments of the universe, its composition, and how it has changed over time is encoded in their properties. Scientists are able to uncover mysteries regarding the genesis of structures, inflation, and the origin of the universe by examining these primordial photons. These individuals are messengers from the beginning of time, and they serve as a link between us and the universe's fiery origins. It has been more than 100 years since the first observations of cosmic rays took place. There was a strange radiation that scientists observed penetrating the atmosphere of the Earth in the early 1900s. After a long time, they were able to determine that this radiation was caused by cosmic rays, which are particles of high energy that originate in outer space. Traveling at speeds nearing that of light, these very energetic particles, which are primarily atomic nuclei and protons, are in a state of continual bombardment. The extraterrestrial origins of cosmic rays were confirmed by the findings of early studies conducted by Victor Hess and other researchers, which demonstrated that the intensity of cosmic rays increased as one ascended to greater altitudes. Scientists continue to be fascinated by cosmic rays today because they provide information that can help them understand extreme cosmic occurrences, such as the jets of black holes and supernova. Their finding was the first step in establishing the field of cosmic ray physics, which connects the Earth to the high-energy processes that are occurring throughout the cosmos. The extent to which we are able to look into space and time is restricted by the cosmic horizons. The age of the cosmos is not infinite. It is estimated to be around 13.8 billion years, which means that the light from beyond a certain distance has not yet had enough time to reach us. The edge of the observable universe is defined by this limit, which is known as the cosmic horizon. The vast span of space and time that exists beyond this horizon remains unexplored. It is possible that this expanse contains an infinite number of galaxies and secrets. We are able to perceive objects that are located farther away as the horizon gradually expands as the cosmos continues to age. Nonetheless, the expansion of the universe means that there are some areas that will remain permanently out of reach. The cosmic horizon serves as a reminder that the universe is significantly more expansive than the part of it that we are able to witness, and it also imposes basic restrictions on the amount of knowledge that we may obtain. The cosmic microwave background, CMB, provides a glimpse of what the universe looked like in its early stages. A weak, consistent glow permeates the universe, filling all of space. This glow is referred to as the cosmic microwave background radiation, an artifact from the time when the cosmos was around 380,000 years old. During this period of time, the universe had cooled to a sufficient degree that photons were able to travel freely, which resulted in the creation of a snapshot of the cosmos in its earliest stages. Subtle temperature fluctuations are carried by this radiation, which reflects the density variation that seeds galaxies and large-scale structures. The cosmic microwave background is an essential element of contemporary cosmology, since it is a source of priceless insights into the composition, age, and development of the universe. These insights are gleaned from detailed studies of the cosmic microwave background. The earliest moments of the universe can be revealed through the study of polarization in old light. In addition to its temperature, the cosmic microwave background radiation displays polarization, which is a pattern in the orientation of light waves. Information regarding gravitational waves and density fluctuations that occurred during the universe's earliest moments is encoded in this polarization. Scientists are able to evaluate inflationary theories and gain a better understanding of how primordial fluctuations evolved into galaxies and clusters by studying these patterns. Measurements of polarization provide a one-of-a-kind glimpse into the physics of the Big Bang, which in turn provides insights into the creation of the universe and the forces that have influenced its evolution. The majority of the ordinary matter in the cosmos can be found in cosmic filaments. Galaxies are organized into clusters that are situated along enormous filaments, which are made up of dark matter, gas, dust, and conventional or baryonic matter. The large-scale structure of the universe is created by these cosmic filaments, which extend across millions of light-years, whereas the majority of the mass is made up of dark matter. A significant portion of the common substance that makes up stars, planets, and life is contained within filaments. This issue arises as hot, diffuse gas between galaxies, which makes it difficult to identify in many cases. Scientists are able to follow the movement of matter throughout the cosmos and determine how galaxies evolve within this huge network by gaining a better understanding of filaments. Jets that originate from black holes have the potential to extend for millions of light-years. It is common for supermassive black holes located in the centers of galaxies to generate jets of charged particles that travel at speeds that are close to the speed of light. These jets have the ability to stretch across millions of light-years, which allows them to sculpt the intergalactic medium and influence the process of star formation in the galaxies that host them. Jets control the evolution of galaxies by heating and displacing gas, hence limiting the uncontrolled production of stars or the triggering of new bursts of star formation. These enormous jets of matter provide us with insights into the tremendous interplay between black holes and their cosmic surroundings, which in turn reveals some of the universe's most dynamic and energy-intensive processes. The ancient light that we sense today bears faint signs of inflation. The cosmos underwent an exponential expansion during the short period of time that is known as the cosmic inflation. This expansion caused microscopic quantum fluctuations to spread out to magnitudes that were macroscopic. Galaxies, clusters, and filaments, which are all examples of cosmic architecture, all have their origins in these fluctuations. The cosmic microwave background radiation, which is made up of subtle patterns of temperature and polarization fluctuations, still contains the imprint of inflation which is inscribed within it. Through the investigation of these microscopic traces, scientists are able to get a better understanding of the universe's earliest moments and the principles that govern its fast creation. The legacy of inflation connects the quantum realm to the huge universe, which demonstrates the profound connection that exists between the smallest and largest scales of nature. It is possible that cosmic rays have a role to play in the development of clouds on Earth. There are some scientists who suggest that the temperature on Earth is affected by cosmic rays because they have an impact on the production of clouds. Molecules become ionized when cosmic rays enter the atmosphere of Earth. This creates charged particles that have the potential to serve as the seeds for cloud droplets. As a result, clouds have an impact on the temperature of the Earth by reflecting sunlight and trapping heat. Cosmic rays are a subtle connection between events in the distant reaches of the cosmos and the climate system of our planet, despite the fact that the degree to which this influence occurs is still a matter of discussion. The intricate relationship between space and the ecosystem of the Earth is brought to the forefront by this fascinating potential. cosmic filaments outline the route that galactic movements will take. Rather than moving randomly across space, galaxies follow a path following gravitational currents that are defined by the filaments of the cosmic web. Over the course of billions of years, these massive strands of dark matter and gas galaxies have shaped their courses toward dense clusters and voids. The large-scale structure of the universe is formed by the influence of this flow on the interactions between galaxies, their mergers, and their evolution. When astronomers create maps of these cosmic highways, they are better able to comprehend the forces that are responsible for building the architecture of the universe, as well as the dynamic motion of the various components that make up the universe. Neutrinos provide us with insights that can help us understand the earliest stages of the universe's existence. During the initial moments of the universe's existence, neutrinos were formed in enormous numbers. These particles are extremely small and have almost no mass. In the moments immediately following the Big Bang, these mysterious particles broke away from matter. Since then, they have been streaming across space with barely any resistance. Although they are challenging to detect, relic neutrinos provide a wealth of information that is extremely useful for understanding the origins of the cosmos, fundamental physics, and particle interactions that occur at extremely high energies. Scientists are able to examine settings that would otherwise be unreachable by studying neutrinos, which offers them a one-of-a-kind opportunity to gain insight into the origins of the universe and the principles that govern it. At this point, the immensity of the galaxy starts to gradually recede into the background of your thoughts. You have made your way through 100 silent wonders, ranging from the brilliant brilliance of newborn stars to the hushed shadows of ancient galaxies. You have flown through starry nurseries, soared along dazzling spiral arms, and beheld the core of the universe shimmering softly across immeasurable distances. From the faint whispers of cosmic background light to the intricate web of dark matter, you have seen it all. You play a role in this narrative that spans the entire universe, a participant who is interwoven into the tapestry that is composed of stardust and time, rather than simply an observer. The atoms that make up your body were created in the furnaces of stars that existed long ago. The explosions that occurred far away in the past have left their mark on the air that you breathe. The universe itself is a member of the same family tree as every single aspect of your being. It was created from the same primordial stuff that currently flows across galaxies and drifts in interstellar clouds. While you are resting tonight, the universe will continue its silent progression through time. The process of star formation is underway. The movement of light is in progress, and cosmic dances continue to play out in quiet harmony. You are a little, loving presence who quietly floats among the stars in this huge, dazzling sea. We appreciate you accompanying us on our adventure across the cosmos this evening. I hope that you have a peaceful night's sleep and sweet dreams. I wish you a good night's rest.